So last week we started the journey of trying to use actual data that we need to maintain its privacy in a way that keeps the released information private. And we started with the extremely simple task of estimating the mean and then the median of a single parameter. So the running example we're using is some data set that was released by the Central Bureau of Statistics years ago, the Fulton data set. And we started with the salary, right? This is a very natural quantity that we may want to estimate. So we would like to eventually predict the salary given some features of the user, let's say. And so this is the data we want to use for that. And perhaps the most basic step that you do before you start training a neural network or something like that as a statistician is like, wait, let's figure out what's going on with the data. Like, what is the typical range, what are the quantiles, what is the mean, etc. And even that very basic task turned out to be non-trivial, and we spent a whole lecture covering how do you do these things. And from my perspective, the take-home message was we don't necessarily need to invent complicated, fancy algorithms. In fact, all of the algorithms we considered were only a combination of two base algorithms, the noise addition, which we use Gaussian, and the exponential mechanism. And the wisdom is in using it the right way, where the right way can be composing it several times in a smart manner such that gradually your sensitivity decreases. It could be that you rephrase the question in a way that has a better privacy utility trade-off, etc. But this is, in a sense, most of what, a big portion of what current research in the privacy world is not coming up with a new base mechanism. To some extent, you might claim that we haven't invented almost any new basic mechanism for years. All we do is either do some pre-processing, post-processing of the queries in a way that induces a better privacy utility trade-off, combine the base mechanisms to produce a mechanism that better suits our needs, improve the analysis to, let's say, identify that we're not in the worst case setting or something like that. This is basically what is done. Okay, so we did that, and we managed to estimate the mean and the median to a reasonable extent in reasonable parameter regimes, right? We said that, of course, there is always a worst case pair of data sets for which the privacy utility will be bad, but as long as we're not in that world, we're happy from the utility perspective, and the privacy is maintained because for any data set we will have privacy. And just a reminder, the way we managed to estimate the mean was by the best method, that at least that's what it seemed empirically in the example that we considered, was privately estimate two quantiles, and then clip the data to those quantiles, and then privately estimate the mean on the truncated data. That was our method. So in this lecture, we would assume that we got an estimate of the private mean and of the mean and of the quantiles. For simplicity, throughout this lecture, I just fixed them to be the true mean and quantiles of the underlying distribution. In practice, of course, we got some noisy measure of them, but we're not dealing now with the question of how accurate those parameters were. We estimated them in the previous step. We have some numbers which we trust, and from now on, we operate with respect to those numbers. Okay, so this is the second. So as a statistician, one of the most natural things you would do once you have a few basic properties of some feature, let's say its mean, its some of its moments, etc. It's basically some moments and some quantas in a way. The next thing that people typically do is something of the sort of find correlation or separately estimate the parameter on different subsets. So in this case, let's say I want to estimate what is the salary disparity between men and women. Okay, the most basic second step I think we can think of. So for simplicity, throughout this lecture, we're using truncated and normalized data. What do I mean by that? So every value, every salary that we have, like someone earns $150,000 a year. First, we truncate it to the two quantas that we found. So if the 95th percentile is 120, so 150 becomes 120. The second thing is that we normalize it by the average salary over the entire population, just because it's easier to have, like, otherwise we will have numbers that are like 12,000 and you won't necessarily understand if it's big or if it's small, how to reason about it, because you don't necessarily know what is the typical range of the salaries. So I'm normalizing it. I want to make it clear, these steps that I just mentioned have nothing to do with the privacy analysis and the challenges, etc. It's just a rescaling of the utility and of the parameters. So it's only here in order to make the numbers on the board more convenient. That's it. So here's the first task. I clipped and normalized all of my data. I'm already in this more natural world. And now I want to ask the following question. I know what's the average salary over the entire population. I want to know what is the average salary over a subgroup. So typically we would ask questions like, what is the difference between the average salary of men and women? Or some, racial minority in the rest of the population, or something like that. Okay, this is the type of questions we would ask. What will be the sensitivity of this statistic? Right, so just to make sure, this is our statistic. I sum the xi's here are already clipped and normalized. So I sum these values and I divide it by the number of sum the values for the rows that belong to group 1, group A, and normalize it by the number of elements in group A, and then subtract the same for group B. Again, I'm taking the simplest thing I can consider, so there's only, the groups are binary. You're either a male or a female, in a certain minority or not. I'm not even going further than that.
So we should think about the subgroup as subpopulation, as
Yep.
fairness, and not like groups. It doesn't have any connection
To group from group theory? No. Group as in the
sense.
in the sense of like the literal sense, like a group of people. So yes, some subpopulation. But in this context, I don't care about what is what meaning does it carry about the world. Like it's all the people that have odd, like their age is odd or even. Like I really don't care what does it mean. It's just like some subset. So my question is, what is the sensitivity of this statistic? I want to add noise that scales with the sensitivity. Well, what is the sensitivity of this statistic?
With the relative size of the subgroup.
Okay, why should it matter? So well, let's go one step back. I changed a single element. Since from symmetry I changed an element in A, right? It won't matter up to the sign. So I changed an element in A. what changed in this quantity?
Oh, either the plus or the minus.
Let's say I had, for simplicity, let's say it's add remove. It can also be a substitution, but so I added or subtracted a user, an element from this group. What happened to the full term? What is the effect? So first of all, one element is subtracted, so that xi is removed from the sum. But there's another effect. The number of elements now changed by 1. So I changed both the numerator and the denominator. Okay. When will this effect will be the largest?
There's only one element, and it's infinite.
When the denominator is small, right? Because when you have a ratio, it's always easier to change the ratio by changing the numerator the denominator when the denominator is small than by changing the numerator. So, right, changing the numerator you need to change by a large number. Changing the denominator you can change it by very little if you are close to 0. So in the extreme case, indeed, if the sample size is 1 and now you turn it to 0, so it became infinity. But you know, okay, you can say it's 0 for 0. So, but if it's 2 and became to 1. So let's say if your neighbor is the maximal value, and you just made it, instead of being divided by 2, it's divided by 1, you significantly increase the effect. So typically what people also do is they don't really have the risk of dividing by too small of a number, so people have like a maximum, like when you normalize by something that's not too small, but still will have the same effect. So it turns out local sensitivity is this quantity, B is this range on xi, like the normalized whatever, and this is what you get here. So it's the either 1 or the maximum of the maximum between the gap and 1. So you can't have 0, but you can have it can be 1 over n, and it can be 1 over a million. So in a sense, my global sensitivity, the worst case over all neighboring data sets, is that I have the range, there's this B, and I can't divide it by any n, because in the worst case it's divided by 1. Right? If you had, basically if group A had 2 elements, one of them its xi was 0 and one of them its xi was equal to B, and I removed the B, so the average changed from B over 2 to 0. And in fact, if there was one element and it was B and I removed it, so the average now changed from B to, well, now you need to define what you do with 0 over 0. Let's say if it's 0, so it's changed from B to 0, etc. Okay. So, the local sensitivity might be small, might be large. The global sensitivity is the supreme. Overall local sensitivity is large. So just to be sure, because like I haven't formally defined what I mean by local sensitivity. So local sensitivity is for a specific data set. What is the worst case that can happen by changing one element, adding, removing, subtracting? And global sensitivity is for any neighboring data sets. Now, here is the natural temptation. When I get a data set and I want to release some private information, it's very clear that I need to consider the worst case over any replacement that will happen with my element. Like any of my elements might be removed, any of the elements that is not in my data set might be added. That's fine, like I accept that. But why should I account for pairs of data sets where none of the two is my data set? Like, let's say the worst case data set is like some combination where let's say, as we said, one of the data sets is, one of the subsets is really small. Okay? But I sampled a bunch of elements, and let's say I chose the two groups to be men and women, and they're about 50-50, so my data set is of size 1,000, and I have about 500 and 500. So why shouldn't my sensitivity scale by about 500? So this is the overarching goal of this first part of this lecture, is to understand if and how can we go beyond the worst case analysis based on looking at our own data set and saying, hey, maybe there is a terrible pair of data sets in the world, but we're not one of them, so maybe we're in better shape. Okay? This is the general goal. So first, again, as usual, let's see what happens. So here we see the distribution of the salary gap between men and women. Okay, this is normalized. So 1 is equal to the average salary of the population. Okay, and the gap is 0.55, give or take. It sounds really crazy, but I didn't include a bit of are you employed. So it's average over everyone, including people who are not employed. There are more women that are not unemployed, so that's right. So they don't dig too much into the meaning of these numbers. It's like, okay, so this is an average. And then if I took a sample of 1,000 people and computed this number, this normalized clip gap, this is my distribution. Okay, not surprising. This is an unbiased estimator and everything's okay. And good. For comparison, because as we said, the size of the small group of the smaller group of the two will be very important. I considered a different binary predictor, which was, are you Hispanic? And there's like about 5% of the population are Hispanic. And we also have a distribution, but notice something. Two differences. One, the average gap is different. The scale here is the same. Okay, so the average gap is different. Yeah, sure, like different populations, different properties. Nothing is surprising here. But the width is different. Right? This is more concentrated, the male and female are more concentrated than the Hispanic population. I mean, the gap, Hispanic versus non-Hispanic. Any idea why this is the case?
Less data, you need to be more smeared out in order to get privacy?
So, no, there's no privacy here. These are both of them just two empirical distributions.
With less data, then you just have less.
No, it's the same. Both of them, it's 1,000 people per sample.
But one of the data sets is smaller than the other thing, so it's a relatively small sample.
What do you mean? No, it's the same data set. The full distribution is the 25,000 or whatever it is.
Okay.
People in the full table that the census released. So I treat it as though it's the population. In both plots, I sample 1,000 people. Like each point in this histogram is 1,000 people that I sample, and I estimated this gap on those people, and I repeated this sampling of 1,000 people many times in both of the plots.
The visual plot you had, the 5% minority was more erratic, you could say?
More what?
Erratic. The results you got for the minority was more erratic because they were a smaller percentage of the data set.
Okay, so intuitively speaking, you say, if I'm trying to estimate some quantity, comparing two groups where both of them are relatively well represented, I'm in better shape than if one of them is not.
Yes.
That is true. And my question is, do you have some mathematical known phenomenon that this directly
More
maps
large
to?
numbers. If you have more of them, then they're more
Sort of,
concentrated.
but there is like what you're saying is correct in the sense of the phenomena that I will mention in a moment that you're probably familiar with is true in a sense because of that. But there is like a much more concrete example that is directly maps to that. What is the variance of a binomial with small probability and large probability? And then what happens when you do the inverse of that? So we know that a binomial with small probability has a lower variance, right? It's p times 1 minus p. But once you look at the inverse of some random variable, so the closer it is to 0, the bigger the variance is. So this is exactly what we have here. Because the numerator is not very different, but it's in all of them people earn 50,000, 100,000, whatever. The numbers are the same scale, but the numerators are different. So if here there are 5% of the population in one of them, so if I sample 1,000 people, so on average I'm supposed to have 20 people. So now the variance of sampling 1,000 times and computing 1 over x for something that has probability 5% is going to be much larger than if it's the probability of something that has half. So this is exactly the same thing that we're used to with the variance determined by the probability, which is smaller in a binomial case when the probability is smaller, but if it's the inverse of that, then of course it's larger. That's basically what happens here. Okay? And that is important for two reasons. One is because if our privacy price will be larger when there's a smaller group, at least to some extent that is okay. Why is that okay? Because also the statistics will have the same phenomena. So again, depends how bigger we are, etc., but it's doable. And the same thing, and the other thing is that that this insight of larger statistical sensitivity sort of going hand in hand with larger privacy sensitivity is a very good hint to things that we will see later. So it is not identical. These are two different quantities, but they have a very strong relation. And the two quantities I'm referring to are the sensitivity in the sense of privacy, which is supremum overall neighboring data sets, blah, 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 how much the quantity changes by changing the element. And sensitivity in the sense of generalization or statistics, which is something like how much does my evaluation typically change with a change of a typical element. The latter, give or take, corresponds to how much noise will be in my estimation, statistical noise, or in other words, you can say what will be my accuracy, my generalization ability. And the first one is to how much noise I will have to add for privacy reasons. And the fact that they're somewhat related to each other explains in a way why, if we work in the right way, we can go way beyond the worst case. Okay, so what do? We understand that there's global sensitivity, there's local sensitivity. Local sensitivity can be reasonable, global sensitivity can be terrible. Okay. Option 1, add noise that scales with a global sensitivity. Yes, it's specific. We always need to do this in privacy. Step 1, as long as you do have some naive, pessimistic algorithm, start with that. It has some trade-off, might be terrible, but that is our baseline. From now on, we start climbing. In this case, the baseline looks so ugly that it's somewhat hard to even understand what I'm showing here. But you remember last lecture we saw 3 plots, 3 lines for each one of them. One is the gap between the empirical population and the distribution. One is between our release and the empirical one, and one is between our release and the distribution. So what we have here is this is the noise of the estimation, which looks like just one line because it's so narrow, and the bottom are two lines. But basically, what I'm saying is like it's so far away that it's just ridiculous. So you might say, okay, I have the local sensitivity. I'll add noise as scales with the local sensitivity. Okay, let's see what happens. So here is an example for a typical data set with here the distribution is the subgroups are defined by 6. So they're typically about half and half. And as you see, these are two relatively similar distributions. They have the gap is not very big. So the gap here, remember, is truncated and normalized, so it's not too big. It's divided by this 500, give or take. Looks good. What happens here? Here, it's the same thing, but with what do I want to say? Sorry, with the Hispanics, and it looks different. Now, why is it different? Because we're basically having here again the same effect as we had in the last week, with where we tried to calibrate the noise to the empirical quantiles or empirical standard deviation, things like that. If you protect your parameter, your statistic, whatever it is that you're releasing, and you scale your noise, or even more generally your randomness, to the local sensitivity, you have the problem that the local sensitivity itself is a sensitive quantity. So if I change a single element, I changed my quantity, but I also changed my local sensitivity. So in this case, where it's easy to show it, the mean will change by much less than the width of the distribution. But no one guarantees that the variance will not change by a lot. And this induces a terrible ROC, which that we saw in the previous lecture. So what I want you to keep in mind is that the problem with scaling the noise with the local sensitivity is exactly the same problem that we have when we propose to scale the noise with some truncation property like the standard deviation, empirical standard deviation, or empirical quantiles. It's the same thing. Yes, you are guaranteed that by changing a single element, the mean will not change by more than whatever it is that you estimated based on that quantity, but that quantity that you estimated itself might change by even more. And therefore you have trouble and the ROC will be terrible. So what will be the solution? If the problem with scaling my noise with a local sensitivity is that the local sensitivity itself is sensitive, the same way that scaling my noise to the quantiles was problematic because the quantiles themselves are sensitive. So how did we solve it last week?
I don't know if it's relevant for the previous week, but if you know like how sensitive is your local sensitivity, maybe you can use it.
Exactly. So if the local sensitivity is way too sensitive, we're in trouble. But if the local sensitivity is not too sensitive, we can do something. what can we do? There are several options. Option one, privately estimate and release it. Right? What did we do last week? We privately estimated the quantiles, released them. Now that they're public information, I can do whatever I want with them. So that is one option. What will it correspond to in our case? Since the local sensitivity here is basically a function of what?
The percentage.
Of what property of the data?
denominator, basically.
The
How many there are.
The sample size of the small group. Okay, so this is the count query. Right? So we can release the count query with adding some Gaussian, Laplace, whatever noise, normalize by that, and move on. That's one option. That will exactly correspond to what we did last week. We privately estimated the standard deviation or the quantiles. Once we paid like half of the privacy budget or something like that for that part. Once we paid it, we have this information. Once we have this information, we can continue as though this is public information. That is absolutely valid. But this week, we will consider also a few somewhat more tricky techniques. Unfortunately, I'm sort of spoiling it. They won't show a significant advantage. It's somewhat hard to find. There are, but like I haven't found yet a easy to show pedagogical example where it's clearly the more sophisticated ones dominate. It's not like they always lose to the naive thing, but
Are there clearly shown scientific examples that work, or it's just...
So, no, there are, again, depending on your definition of natural or not, depending on your definition of significant difference, there are, like, these techniques are cool. I mean, one of them is used more than one of them is used very frequently, but in a specific way. The other one is not as frequently used, but they're all important tools that we should know. Okay, so step one is what I proposed. Privately estimate the count, and wait, I think I lost the there was supposed to be a plot. Let me see what happened. Yeah. Okay. Same one as we have here. We were supposed to have one for noisy count. Right. So the idea is very simple. Split your probability in half. Your epsilon in half. Half of it you spend on estimating the count. Half of it you spend on estimating the mean once you know the count. Basically, you estimate the sum, and since you know the count, you divide by that. And okay, now where will I check it? So here's the interesting thing: if I check it in for a data set or for population where the probability of getting the probability of the smaller subset is very small, like even smaller than 5%, then I'll have terrible statistical validity. If I will check it for like a data set where it's 50%, then it's not interesting because this is a very easy problem, even for privacy. So I chose because here I'm working with a data set of 1,000 people, so I chose examples where the data sets differ by the size of the smaller group is like 50 to 100, which corresponds basically to 5 to 10% of the population. So this is give or take where we're at. So there is a significant degradation, but not completely unreasonable. Like here, we couldn't even see what's going on, and here, so the spoiler is that it will look about the same thing. So again, this is a much larger distribution, right? So the noise is larger by a factor of, 3 or 4. Your accuracy degraded by a factor of 3 or 4. But okay, 3 or 4, not 100 or something. Okay, and again, as usual, we don't see here the difference between the two lines, because what happens when you have, what we have here basically is the third line, the continuous line, the red line, would be the convolution of the previous two, right? Because it's the sampling noise plus the privacy noise. So when one of them is significantly larger than the other, then the convolution looks like the larger one. So this is what we have here.
But can you theoretically just ask the sum, privately check the sum, privately check the number, privately check the sum, privately check the number, and then just divide, and do this, and do the whatever?
Yeah, this is the.
That's what you're doing.
Yeah, I separately compute the count and the sum,
That's what you're doing.
pay the privacy for each one. Yes, so I moved to the next one because unfortunately I somehow lost the plot, but it looked very similar to that. So, but why is it still significantly worse? Because I chose a setting where that sum in one of the two numerators is it's not tiny, but it's relatively small, like 5 to 10%. Because that's the problem. There are different regimes, and in each one I would give you a different plot. So I chose one where it's not so small that even the statistics won't work, but it's not so large that it's going to be very easy for privacy. Had I chosen for 500, the price will be lower.
If the number's bigger and you really can't get privacy, well, you're asking too precise data, well, go jump in the lake.
No, but I chose a intermediate. So there is that's one of the things I'm trying to figure out, what would be the right plot to do it. But basically, if your x-axis is the sample size of the sample the probability of the smaller population, and the y-axis is your accuracy. So in any case, the smaller the probability, the lower the accuracy, right? That we expect. But the rate in which it decreases for private and for non-private algorithms is different. So if it was 50-50, which means both data sets were about 500, the private distribution would look very similar to the non-private one. If it was 1% or 0.5%, then both of them would look terrible. But then in this intermediate regime of like 5% or 10%, then privacy does degrade in a non-negligible manner, but not like overwhelming. It's just
a
bad.
percentage issue, or is it just a raw numbers issue?
No, so I fixed the sample size to be 1,000. Of course, as you said, I can also fix the probability and vary the.
Isn't there something where private stuff degrade or private stuff get improved, like the square root of whatever non-private stuff improve or something like that?
So okay. Generally speaking, statistics improves as a square root of n, and privacy degrades as n. I mean, sorry, it's like statistics, the error decreases 1 over square root of n. That's all the concentration we're used to. And privacy degrades with the sensitivity, which is 1 over n. Okay? So for large enough n, privacy almost always becomes negligible. But that's the point. When you have a small subset, a small population, and your full data set is not very large. So again, in this case, the n that we're trying to estimate, which is the numerator of one of the two, is 50, or sometimes even smaller, right? Because statistics, sometimes 20 or 30. Okay, 30 is a small enough number where the difference in constants and what you get from the epsilon and delta and whatever is more significant than the difference between square root of n and n.
Yeah, what I'm saying is, could it be that is a core feature when you're trying to do statistics privately, that the slope is off by the square root of n? And in the specific range in which you check, the square root of n is the issue. Like, it's the dominating factor.
I think what you mean is the other way around. It's because statistics improves at like the square root of n, and privacy improves like 1 over n, when you are in the large sample size regime, privacy is not a problem. So the problem is not that square root of n is big or small. The problem is that at this point, 1 over n is not much smaller than 1 over square root of n.
Okay.
The advantage of small samples. Now, I wouldn't say it as a general rule that always holds, because not every private mechanism scales like 1 over n, and not every statistic scales like 1 over square root of n, but this is a very, very common phenomenon. 1 over square root of n is basically whenever you're in a CLT regime, then you are in the square root of n regime. In privacy, all of the linear and linear-like queries have a sensitivity that scales like 1 over n. But again, not everything is linear.
You need to add in an extra square root of n noise on average, at least in order to be private. And we've proven that basically with the whole, you have the vector, you just ask for queries and...
Yes, but even that is not a completely general statement we can say, because we don't know that it's true for, I don't know, k-means. What is the amount of noise or whatever? How do we even define noise and utility in clustering, right? Like, it's not everything fits that mold, but yes, you are correct that in the context of linear and linear-like queries, the reconstruction attached showed that if you add noise that is less than square root of n, then you can fully reconstruct the data, and square root of n is anyway what statistics gives you, so you need to be able to add something that matches what you get from there. But okay, again, like I'm hesitant to say it because like under sufficient restrictions, there are very clear statements you can say. In the very general case, no statements. So, okay, but the intuition is important here. Okay, so that was the first step. Estimate privately all of the components, and then in post-processing, do it. As a side note, even if as a privacy person we reach the conclusion that this is it's a valid thing and maybe a good idea, it still leaves a whole question open, which is now what is the best thing to do from the statistician's perspective? No one said that the right thing to do from the statistician perspective is to say, okay, I got numbers which are not the true numbers, they're noisy approximations of those numbers. I will hope that this noise is not too big, and I will continue my statistical analysis as though these are the correct numbers. This is not necessarily the right thing to do. If you're trying to estimate a ratio, and you know that both numerator and denominator you got a noisy approximation, maybe there's a smart thing you should do. Maybe you should debias somehow, maybe whatever. So there's this whole different line of work that statisticians do now these days, which is, okay, given that someone released some output from a private mechanism and I want to run some statistical process over it, what is the right way to do it? And the answer is not always just treat it as though this was the correct number and just incur some error. Okay, so that was option one. Here's another proposal, which is, I think, very natural. Say I want to do this estimation for the gap, not for Hispanics, but for men versus women. I don't know that the data set that I got has fraction of men and women very, very close to 50%. But with high probability, this is the case. So, from privacy perspective, we cannot have a step in our analysis that says, well, since about half of the population are men, with high probability, my data set is also about half and half, blah, 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 right? Like, that's not a valid argument in the privacy analysis. But in the statistics analysis, that's of course, like, if I give you an algorithm, then I tell you, look, if more than 55% of the data set are men, or if more than 55% are women, things will go away. But if we're close to 50-50, then my algorithm will be great. As a statistician, you'll be happy with that, right? Because anyway, you have other guarantees that tell you that with high probability, your proportion is correct. So if I know that this is probably the case, and if from privacy perspective, what to do if this is the case is easy. So here's a variant of the original proposal, which is estimate something privately and then continue. Estimate privately whether we are in a good shape. So now I don't need to spend my my budget on estimating whether what exactly is the sample size. I just ask, is it above certain threshold or not? And that is something that we can do cheaper, typically, depending again on the situation, whatever. This case, not so much because it's count, so effectively is the same, but this is basically the idea. So now we would say, look, my guess is that we will be, the smaller data set, the smaller subset will be at least 350. Why? Because I have some prior about the data. I know what kind of group am I asking? Is it Hispanic, or is it men, or is it people under the age of 40 or whatever? So I do the following thing. First, I check whether indeed more than 350 people are in the smaller group. Second, I release the private quantity with sensitivity that is scaled to 350. Again, if I estimate it in a non-private manner, so we would be exactly, and what do we do if not? So it's up to you, but we can just either output a random number or just report help. Like just say, hey, there's a problem in this case, it didn't behave as we expected, or whatever. So, if I did this check in a non-private manner, then again, privacy would leak by this check because I'll have two data sets, one of them is exactly below, one above. Here I would release a random number, and here I would release like a noisy estimate of the data set. But if I will do that in a private manner, I'm good. So this method is called proposed test release.
You will pay by composition.
Yes, always. Same way we paid for estimating the first quantity in there, but we can pay much less in many cases because checking if something is problematic can be in many cases done in a cheaper way from privacy perspective than estimating a quantity.
Well, you need more than one binary query in order to get a definite answer.
Yes, but binary query is not always cheaper than estimating a quantity.
Yeah.
Like when you estimate a count, it's about the same. But again, it depends on settings. As I said, I'm somewhat annoyed by the fact that I haven't found an example that is both very clean and natural and at the simultaneously shows exactly the different effects. So I'll just show what happens here. So now utility is a bit annoying because utility is not only your accuracy, you also need to ask with what probability I will refuse to report an answer even though I should have, or vice versa. Right? So if you say that even when I refuse, instead of just reporting that I'm refusing, I'm just releasing a random number or something like that, then you have like the classical accuracy. But then it depends on like what kind of distribution you sample from. If it's typically what we do in the utility analysis, we say, hey, here's the failure probability of us refusing to reply even though we should have, and then the rest. So obviously it will drop very quickly. So here the threshold is 30, and if that is what I want, so very quickly the probability of claiming I can't reply drops, and as you see, it's more noisy, not by crazy amount. Again, because I chose threshold 30 and the actual one is 60, so there's a gap, between 50 and 100. Right? So this is proposed test release with a somewhat pessimistic number. Because proposed test release, remember, is parameterized by something which is what is my guess. If my guess was exactly the right one, I'll be in better shape than if my guess is the wrong one. The more pessimistic I am in my guess, the worse amount of noise I added even though I didn't have to. The more optimistic I am, the higher the chance that I'll just miss the mark and and I will refuse. So that is why we have a trade-off.
Okay.
Questions? Or, okay, can take a break.